Our goal as solar cell engineers is to convert as much of the light incident on the surface of our solar cell to usable electrical energy. The first step in any road to improvement is identifying the obstacles. In this video, we will therefore provide an overview of the optical losses in solar cells. There are many solar cell designs for a wide range of applications, but whether we are designing high-performance solar cells to power space exploration or thin, flexible solar cells for building integrated applications, all solar cells are subject to the same set of design rules. Optimizing design of any type of solar cell involves a delicate interplay between three concepts. These are shown in the figure. Spectral utilization aims at using as large a fraction of the incident solar spectrum as possible. Band gap utilization involves the collection of the generated charge carriers. It therefore considers the electrical losses in solar cells, which determine the voltage generated in reference to the band gap. Finally, given a certain semiconductor absorber, light management focuses on maximizing the absorption of light and subsequent charge carrier generation in the photoactive layer of the solar cell. The band gap utilization has been discussed earlier in this course. Therefore, in this video, we will focus on spectral utilization, and in the next video we will focus on light management. The learning objective for this video is to understand the loss mechanisms that limit the spectral utilization of a solar cell. We will learn how this fundamental limit depends on the absorber material and how to calculate the fraction of the solar spectrum that can be utilized. Finally, we will look at the optimal bandgap energy for a single junction solar cell. Any single junction solar cell can only utilize a fraction of the incident energy. To visualize this, we will take a look at the band diagram of a semiconductor material. The blue box represents the valence band. The valence band contains the allowed energies of the bound valence electrons in the semiconductor material. The yellow box represents the conduction band, which contains the allowed energy levels of the unbound electrons. The space between the valence and conduction band represents the band gap. The green line is an incident photon. As we recall, the photovoltaic effect involves the absorption of a photon with an energy that is at least equal to the band gap energy. This excites a valence electron from its bound state in the valence band to the conduction band. The excitation of an electron leaves a hole in the valence band denoted by the blue circle. Of course, not all incident photon energies are exactly equal to that of the band gap. Therefore, depending on the band gap energy, there are three possible scenarios. The photon energy can be less than, equal to, or greater than the band gap energy. We have already seen that when the photon energy is equal to the band gap energy, no energy is lost. Let's now consider photons with energy less than the band gap energy. These photons do not have enough energy to excite an electron from the valence band to the conduction band. Since there are no allowed energy states in the band gap, these photons simply pass through the semiconductor material. The semiconductor material is, essentially, transparent to photons with an energy lower than its band gap. We call this a non-absorption loss. If, on the other hand, the photon has an energy greater than the bandgap energy, some of its energy is lost as well. Upon absorption of a photon, the valence electron will be excited high into the conduction band. Shortly after excitation, however, the electron will relax back to the conduction band edge. The excess energy is thereby converted into thermal energy, and this thermal energy is in fact a loss, since its energy can no longer be utilized as electrical energy after charge carrier collection. This process is called thermal relaxation or thermalization. To put it simply, if a solar cell absorber has a bandgap of 1.1 electron volts and a photon of 1.6 electron volts excites an electron-hole pair, then the solar cell can only utilize a maximum of 1.1 electron volts from that photon. 0.5 electron volts of energy are therefore lost to the thermalization. In later videos we will see that this is an upper limit and solar cells actually extract less than that. But this is a good way to understand the losses that occur due to thermalization. From these two effects, non-absorption and thermalization, we can see that there's a trade-off when selecting the bandgap of a solar cell. If the bandgap is too large, most of the solar spectrum will pass through the solar cell due to non-absorption. If the band gap is too small, the solar cell will indeed absorb a lot of light. Much of the energy of that light, however, will be lost due to thermalization. So how large exactly are these losses? We can determine that using this equation. It shows the fraction of the incident energy that the solar cell can use, indicated by P use as a function of its bandgap energy. Lambda g denotes the wavelength that corresponds to the bandgap energy of the absorbent material of the solar cell. By integrating the spectral photon flux over all absorbed wavelengths and multiplying it by the bandgap energy, we find the amount of usable energy. The fraction of usable energy is then determined by dividing with the total amount of incident energy. This figure gives an impression of the usable fraction. The spectral irradiance of the AM 1.5 spectrum is illustrated by the yellow area. The red area illustrates the fraction of energy that can be utilized by a single junction crystalline silicon solar cell. Such a solar cell has a bandgap energy of 1.12 electron volts, which corresponds to a wavelength of roughly 1100 nanometers. Much of the energy from the short wavelength spectrum is lost due to thermalization. In the long wavelength spectrum, the losses are caused by non-absorption. This figure visualizes the trade-off between using an absorber layer with a large or a small bandgap energy. This figure shows the fraction of usable energy as a function of the bandgap energy of the material. The usable fraction is also known as the ultimate conversion efficiency, since it is the efficiency of the solar cell without absorption or collection losses. Naturally, the usable fraction depends on the irradiance characteristics. Therefore, it differs slightly between the AM 1.5 spectrum on Earth, the AM0 spectrum in space, and the spectrum of a perfect blackbody radiator. The trade-off between thermal relaxation and non-absorption defines an optimal bandgap energy. As we can see, this optimum is around 1.1 eV. Just another reason why silicon, with its bandgap of 1.12 eV, is of such interest to photovoltaics. Gallium arsenide, having a bandgap of 1.4 electron volts, has a high conversion efficiency potential as well. In the second course, we will show a trick on how to utilize more of the spectrum using so-called multi-junction solar cells. For now, it is good enough just to understand the basic concepts behind spectral mismatch. So, in summary, we saw that all solar cells are subject to the same set of design rules, of which spectral utilization is one. We learned about the two main ways that losses can occur due to the spectral mismatch. These are that photons with a lower energy than the bandgap will not be absorbed at all. Secondly, solar cells will lose some of the energy of photons higher than the bandgap due to thermalization. These two processes put an upper limit on the spectral utilization of any single junction solar cell. Finally, we saw how thermalization and non-absorption define an optimal bandgap energy of about 1.1 eV. In the next video we will discuss the last design rule, light management.